Professor Annie Chu from University of California at Irvine, and she's a professor of statistics. So many of us know Annie's work, and she definitely worked not just on the imaging, but she have done a lot of important work in this theme. So.
Everyone can hear me okay? Okay, thank you, Tan and Hong Tu and many others and all the participants. Also, Philip helped a lot. And actually, I never see any other slides from the other speakers for this session, but I was surprised when you will see we are hitting on the same problems. And I have some answer, but not all the answers. Okay. Actually, first, talk about, a lot of us talk about imaging, always talk about medical imaging, right? And a lot of medical images is about brain medical images. Now, why? You have to ask, oh. Is it, okay, is it working? Hello? Can you hear me? Is it working? Oh, the Zoom, they cannot hear. Should I just use that one? Okay, yeah. Okay, sure. So actually today, I'm actually talking about some other imaging, but I'm actually starting with this brain imaging. We work on a lot of Alzheimer's disease, right, ADHD, but I think because a lot of us interested about aging and Alzheimer's disease is a very progressing disease. So this kind of imaging, you see PET images, you will see the progression of the Alzheimer's disease. I would say this is a very classical medical imaging examples. It's just one of the examples. And usually what you see that, this you can see, oh, we have a shrinking hippocampus and enlarging ventricles, right? This is a kind of indication of the Alzheimer's disease progression. Now, this is traditional statistical analysis of what we're doing. Classification, signal detection, involve model selection, spatial statistics, statistical inference. Susan mentioned about the uncertainty, right? Because the statistical inference, we are doing a lot. We answer the question about the uncertainty. But actually, the challenges, right? This is one of the questions. Actually, this also hit on with Martin's question and also Hong Tu's question. We have multi-source of data. Also, people sometimes call multi-modality. We not just have imaging data, MRI data. We also have PET scan, different kind of imaging data. We also have a genetic information and also the CSF, which is biospecimen data, and also clinical data, right? And interestingly, okay, this is another slide. Not every subject have all the measurements. This is just exactly what Martin said, right? And what we see, this is not very typical missing data, what I call the block missing data. That some subjects could have entire columns of data missing. So it's very different from typical missing data we talk about as statistician, intermittent missing or dropout study. And here's like, for some subjects, they have no CSF. For some subjects, they have no genetic information. We have this. How can we do data integration? Now, there are many reasons why we have this kind of data, because you have a high cost to measure. And a lot of times, there's just no need to have this kind of measurements. If you know someone has very severe progression, certain information, it's like obvious. You don't need to do all this kind of test, okay? So how can we do good data integration for this kind of missing data? Now, actually, someone also mentioned about statistician and engineering, CS. We think this kind of problem very quite differently. As a statistician, we have an advantage because when we deal with missing data, we not just think about the missing complete at random. But when I work on some other paper, when I also studied the simulated data based on CS people, I was surprisingly seeing that most of the data, they think missing data is missing complete at random. Now for us, it's impossible. Why? And for this situation, it's actually informative missing, okay? So this is something we can think about our strengths and advantages as a statistician compared to CS or engineering people. But actually, we shouldn't limit ourselves just for medical imaging data, okay? This is the kind of most well-used data in AI or deep learning called MNIST data, right? How many of you, your students, work on this data? I was going to talk about the deep learning. Someone mentioned, right? These are handwritten numbers. Actually, deep learning is doing very, very successfully. I will show later, I will tell you why you're doing this kind of training accuracy is 99%. Even testing, using testing data, it's also close to 99%, right? You're doing all this CNN. But let's say I'm doing some other, in what situation? Some actually, the Muhammad actually asked this question. In what situation CNN could perform really, really badly? This is a very simple example. You generate this data. What does data look like, okay? Now, you might think, because this is something why doing this kind of simulated data? Because a lot of you doing the tumor cancer, the tumor is already formulated, right? I think I always ask myself, if a tumor is already formulated, pretty much every imaging analysis could identify, right? It's no big deal, the tumor is there. But this is something related we call tumor-associated microvesicles. That tiny, tiny microvesicles. Every normal person, we have a lot of microvesicles all over the body. The scale of the microvesicle is very, very small. It's only about 100 nanometers. So small that the microvesicle can go through your blood vessels in and out, okay? So this is the difference between the potentially cancer patient and the normal one. So if someone will eventually develop invasive cancer, they have very high concentration of a tumor-associated microvesicles. It's kind of cancer, the shape, okay? So this is the synthetic data we generate. And it's not working now. So I'm just doing even a weak signal. You can use a Poisson process to generate this data. You're using the CNN, you clearly see that even you have a weak signal or strong signal, your accuracy is not that high. Especially your sensitivity is very low. It's below 20% of sensitivity. Your specificity is high. The true negative is high, but true positive is very low. You will ask why, okay? The reason because it's very difficult to do it because you have very noisy background and you have a high heterogeneity. That every different subjects, their signal patterns are different, okay? So this is a problem. Seems the click doesn't work. Now, this is the real data. I work on this called optical imaging. I think the optical imaging is the most cutting edge medical imaging compared to the ultrasound, compared to the fMRI. So all this with the four modality, they have very intrinsic molecular contrast. Okay, molecular contrast is that they can see different layer or level of a molecular contrast in your body. Some is more surface, smaller, some is deeper. The reason because this is much more high technology. Remember that light, it's a much, compared to the ultrasound, it can penetrate deeper because it's a longer wavelength, right? As the light is much shorter wavelength, it has a disadvantage because you cannot penetrate deeper. So if you want to do the medical imaging, you want to see something deep, doing this light imaging, optical imaging is very difficult. But this one, they're doing the multiphotons, they're able to penetrate much deeper, okay? And also it's label-free, you don't have a radiation, things like that. It's a non-invasive, real-time in vivo imaging. So this is the real data. You have a normal one, have a four modality, and the other one is a cancer one. You can see the overall, the background is really noisy, okay? See all the strong, this line, circle, doesn't matter. The circle usually related to the fat, your fatty cell in your body. And what you care about is a very weak signal background. which is all the dots, right? The concentration and the patterns. This is what we call tumor-associated microvesicles. So if we are able to identify this kind of highly concentrated tumor-associated microvesicle, we are able to eventually to tell that the person eventually will develop invasive cancer before the tumor is formulated, okay? So you can see for this one, what is CNN performance? Actually, we do all kinds of tuning, okay? Your accuracy is 85%, sensitivity is still 70%. Let's say compared to MINISTER data, it's much lower, okay? Specificity, true negative, no big deal, because in cancer study, we really care about the true positive. Of course, we also care about true negative, but true positive is more relevant. You don't want to miss any serious patient. So this is something what, besides the interpretation when you're using deep learning CNN, is like when you're dealing with the small samples, when you have a high heterogeneous population, actually deep learning, this type of a tool doesn't do that well. Well, why? Because they don't have a large training samples. They don't have this kind of uniform signals, and therefore they cannot do a very good job, okay? So this is something. And I'm also going to talk about generative deep learning. Now, when I give a short course about deep learning, this example is always the most kind of a successful story. Talk about how successful a deep learning using AlphaFold, okay? Now, this is the red, the green and the blue. The green is experimental result, and the blue one is a computational using the AlphaFold that can predict it pretty well. This actually is a predict the protein structure of a SARS-CoV, okay, the protein virus. If you look at the surface, you see they're doing really well, right? Especially with the fatty lines, you see they seem to cover very well. But if you look more carefully, there's something doesn't really, it's here, there, it's not really matched. Maybe you think it's no big deal. Now, this is what I want to say something, that the challenge part is a part of the image are important for disease diagnostic, yet they are poorly predicted due to the limited training samples. It's kind of like you have kind of like your outline, right? Like you're doing extreme series, you're doing the risk prediction. It's a large population, you can do very good prediction, but they're really not that important. You really care about their small one. The small one is the one you care about, the like extreme outliers, okay? So in that sense, this also little tails, which doesn't match with the green one, actually this maybe tell us a disease, something different. We actually don't care about the one match pretty well, okay? This is something I think we should think carefully and also challenge ourselves that the fundamental reason that if the training data doesn't represent the testing data, we will get very biased and misleading conclusion, okay? So I think one of the very challenging issues is about integration of the data, integrate the data for the heterogeneity samples. If the samples are homogeneous related, integration is easy, right? That's what we call population model. But if it's a heterogeneous sample, you try to integrate the information, it's very, very challenging. Another thing I want to say about this training data is not representative for testing. You might have heard about that. If any senator of the US, if they're Latino, Hispanic, or African American, you take their mugshot and you put it in the computer, and you know what? They have a high chance they're identified, they're criminals, okay, compared to the Caucasian senator. This again tells you the trustworthiness of AI. Why? Because, right, it's a racial bias, right? When your training sample, your most criminals is it's like a Hispanic, Latino, African American. Then even you put a senator, their picture, even, of course they're not criminals, you will identify them as a criminals, okay? So also we know that in US, all the presidents are Caucasian male except Obama, right? So if you put Obama, if you try to generate Obama, he is not black, he's white, okay? So this is something that if we want to get a trusted AI, we really need to think very carefully, is our training data really representative for our testing data, okay? Another thing I think it's very, very challenging about these days, I think about, because when I'm doing the differential privacy, especially for correlated data, I want to get the synthetic data with the same dependent structure. I run into this problem that how can I generate a density distribution accurately? Okay, this is the same question for image data. This is actually very difficult. In statistics, we always think very simply, say, oh, generate density function. But this is for like a low dimensional, you can generate. But for high dimensional data, especially you have a multi-source, 3D, 4D, 6D, this kind of imaging data, how can you generate this distribution function really accurately? Especially this distribution function can capture the dependency, okay, among the data. So this is what we try to develop as a fair and trustworthy related to in the imaging data. My last slide is a summary. It's a kind of general question. What can statisticians contribute for imaging analysis? I think Martin did a very good job, right? And I think I was inspired by Haldas's brief talk in Lisbon, that we need to ask ourselves, we need to find the most important problems to work with, right? And if we are not working on the most important problem, we need to also ask ourselves, what things prevent us to work on these important problems? Of course, all of you have a different thinking, what are the important problems? I think you definitely should not say, I work on the problems so I can get published, I can get published in top 4 journals, I can get promoted, I can get awards. I feel this is just very, very wrong thinking, right? This is actually during Lisbon workshop, someone mentioned, the COPS committee, someone mentioned, say, if someone is always chasing the awards, this actually devalues the award itself, okay? So I was just thinking about really just for our field, we should say, what are the most important problems we should work on? And why, if we know, what things prevent us to work on these problems, right? And we need to think more creatively, and we try to solve some real problems. And really, I think innovation is very important, okay? Especially like innovative method and algorithm. And in the meantime, we should worry less about developing theory for the purpose of developing theory. Actually, I want to say something. Good theory should play an impact role for the applications. If the theory is not really doing play the important role for the application purpose, I think we're wasting our time to develop this theory, not just pure theory, okay? So again, I want to, lastly, I want to emphasize, we need to utilize our strengths. We shouldn't see, like Muhammad mentioned, I feel dismal because the field of AI grows so fast, right? Especially like ChatGPT, AI things, and we always feel we are left behind. We are chasing something. But in the meanwhile, I'm doing a lot of machine learning problems like a recommender system. I see our strengths, that we actually think quite different from the engineering or CS people. The reason because, like for example, even just I mentioned about the missing data, like I was shocked seeing that all they're thinking about is missing complete at random. I mean, 80% of statisticians now will not think about missing data just for missing complete at random. We have other knowledge, especially, let's say, uncertainty, variation, variability, this kind of heterogeneity, right? This kind of problems. So interpretation, interpretability. So I think there are a lot of work we can develop and really strengthen our field, okay? So this is my end of talk. Thank you.
So we are a little bit behind schedule, but I think we can take one or two questions before we head into the break. Yeah, I have a so go ahead.
So Annie, you mentioned to pick important problem and that solve real problems. And earlier, Susan also mentioned the issue with that students. So how do you motivate your student? I really appreciate when you explain the examples. You sound like you know a lot about the disease itself, about the conditions. So how do you train your student to be more like you?
Very good question, right? Usually, I always tell my students, say, don't just sit inside your room, like Chinese say, 空中造车 means build a car in the air, okay? I say I want to really see, at least find some real data problem, right? So I would say a lot of us new statistical methodology we did in our lab, in our team, that really because real data motivate us to develop a new methodology. For example, the mobile health data, we saw the multi-resolutional data. And it's a very different data that typically we see. Like when I did a lot of longitudinal data, but when I do the mobile health data, I see that we have a multivariate time series data, and as the resolutions are different, cross subjects, they are different, right? And the missing patterns, they are different. So how can you address this type of problems? And I think for imaging, for this photonic data, the optical imaging data, I actually took the initiative, talked to the bioengineering faculty, and then he actually come to my office and say, look, it's my sabbatical leave. I really want to learn statistics as well. So he explained all this optical imaging data to me. So, and because we see this very unique, like a weak signal, but very strong noise background, I don't see this kind of problem in medical imaging like a brain imaging, because brain imaging is a very structured. I know where the hippocampal area is, but for this breast cancer imaging, like I don't even know what this microvesicle, where they're located. Everyone's different. So I really think about, so that's another, like none of my students really work on the same problem. Because once they come to work with me, I say, tell me what area you're really excited about. Some say, I'm excited about causal. I say, I don't do much causal, but it's fine, let's do causal, okay? So we do some causal inference paper. And another student said, I want to work on the network data. I said, I don't have any experience on network data, but it's fine. And then we published several papers on network data. So you will see that my publications like in every area. This is because my students have all different interests. I don't want to tell my students, say, this is my area. I'm comfortable. I really also want to push the students out of their comfort zone. Also, I usually ask them, don't work on the same problems, same type of project for all your thesis. You want to publish 3 papers, best way is to have 3 very different problems. Okay, 3 different, so they really learn. But they also get some disadvantage. You know, if you stick with one, you're already familiar, you do fast. But I really just feel I feel bored. For me, myself, if I work on always same thing all my life, I feel bored, okay? But maybe for other people, I think it's not the same case. So, yeah, so I think, again, the different students, it's a very unique individual. You need to address like a heterogeneity interest and work the best. Like some students, I say, look, some students just not very good at the theory, right? I said, don't worry about it. I said, if you have a strong methodology and innovative idea, we can still publish well. Don't worry about that because you couldn't have a theory, so you cannot publish in top 4 journals. But sadly, we have to say all the biometrical JSSB, JASA, TNM, and also what's the other one? ANOS, right? They all require theory. If you don't have a theory, so that's I just think about that's a problem of a field, right? Even you have a great idea, you cannot publish top 4. I mean, except the JADA have a case application study, right? But that's wrong. I just feel that. Okay, yeah.
So I think, I know there's still a lot of thoughts, but fortunately we have an afternoon breakout session to explore further of the 1 through 6 and then how to train our students to be like Annie, Hongtu, Martin, you know, we can all dream big. So let's take a quick break and come back maybe 11:40 that we can go into the next session. Thank you.